Tag me, Mr. Woolison.
No memes for Mr. Woolison. Or whatever you
Share
said.
your screen. Are you going to share that screen, Mr. Wilson?
Do what?
Are you going to share that screen?
Am I sharing what screen?
Or are you doing a video?
Wait, what?
Are you doing a video?
I'm going to do screencasting because the screencasting works good with the PowerPoints, and then I'm gonna try to like go back and forth between screencasting and teaching on the board. But the screencasting has all the best like quality. So what did you do? All right.
Did somebody just fall over?
He dropped his phone.
Yeah, and it
Oh, that sucks.
Yeah.
I hope it broke.
Don't drop your phone. All right. I'm going to start as I find it. Where is it?
I'm going to use this.
Service. Why is all that there? All right. We are looking at this one. Are you ready? From the beginning. Okay. So, did you take my...
I did. I was going to do it.
You can do it. I don't care as long as you don't go too fast for everybody else. It actually, because half the time I forget anyway. So you're in control, but don't mess that up. Otherwise, I'm giving it to TJ.
TJ knows.
All right.
Wait. Can you give it to me?
Ross, not until you start using a pen.
Well, I guess I'm never gonna do it.
I guess not. Okay, so we're going to go over Introduction to Digital Electronics. It should be the next thing in your table of contents. Make sure you're filling that out. Everybody will be on different pages, so I'm not going to tell you what page you should be on. It just kind of depends on how much you're writing and how large you're writing. So, however, this mask seems to be causing problems.
We have 100 pages in here. I don't know.
All right, we'll try that.
We'll write that.
A little then. Okay. Introduction to Digital Electronics. Here we go. So this is your definition for digital electronics. It's the study of electronic circuits that are used to process and control digital signals. I would write that first sentence down right there. Yes. Yes. Uh-oh. Oh, somebody's in the lobby. I have to go let people in now.
Yeah.
How do I do that without without sharing?
You should just switch back. You should just switch back.
Mr. Butler. Okay. Make sure that you are going.
By the way, do I sound better? Is my microphone better?
I guess so.
I mean, like, I got these new headphones. I want to know if it sounds good.
We can hear you. That
That's
sounds
the most boring answer I've ever.
10 out of 10. I highly recommend. All right, so everybody have that definition? Let's move forward. Okay, digital electronics is the foundation of all modern electronics devices, such as cell phones, MP3 players, etc. The truth is you don't really need to write all this down. You just need to understand that that's where we're headed with all this. Without digital electronics, we wouldn't have all these fun devices that we have now.
I don't know what happened.
What'd you do?
I don't know.
Uh-oh.
No,
Yep.
it's like it just went off my head next. I promise this. No, I promise that happened. Uh-oh. Oops. I know I hit next.
You hit the bottom button that turns it off.
Oh.
Okay. So, now that that's
Did we write
taken
that
care
down?
No. Major focus of DE course is to expose students to the design process of a combinational and sequential logic design. God, I can't even use this thing. I'm gonna have to take this off. I'm gonna have to go get my other mask.
It's like me, face shield.
Yeah.
Oh, man.
Right.
Right. All right. It's making me suffocate.
You should
All
stay
right.
here, Woolison.
Huh?
You should stay here.
Nah,
Why?
no way. Okay, to expose students to the design process.
Wait, what do we have to write down on this one?
Nothing. Just listen.
Oh,
Okay, combinational and sequential logic design, teamwork, communication methods, engineering standards, and technical documentation. Okay, this you do need to write down. Digital device contains an electrical circuit that uses discrete or exact values. So make sure you put down next to discrete exact, so whenever it shows up as a definition, you understand that when they say discrete, they mean exact values in its design and function. Discrete values are going to be listed as zeros and ones.
And 1, 2.
And I'm sure you have heard of this particular system of notation. When you use zeros and ones, what's that called?
Where's code?
Close.
It's,
What is it?
I know.
Come on, somebody knows out there.
I said the answer, so I already tried.
It was close.
Computer
It's
code.
code,
It is, it's computer code. What computer code uses zeros and ones?
a program.
binary.
Binary, thank you.
Binary, thank you.
Thank you. Somebody got it, yay. Yes, so if you haven't figured that out, we will be learning binary in this class. Woo.
0, 1, 1, 2.
There's no two.
0, 0, 0, 1.
What's that?
0, 1, 1, 0, 0, 0, 2.
You do? Good. Yeah, if you have computer science, you'll learn it also. Yep.
Okay.
We only deal with numbers though. We don't deal with alpha characters. So,
What does that mean?
alphabet,
Oh, okay.
letters. 10 is 2. Yeah, 1 0 is 2. Yeah. So if you're taking computer science, you're already getting some of that, which is great. Hopefully, when it comes to me teaching y'all, you'll already know it and you won't have struggle with that.
I might.
Otherwise, if you didn't get it in that class, you'll get it in mine. So,
We do have to take computer science?
do what?
You have to take computer science?
No. All right, moving forward. Binary, yay. Why are there so many digital devices today? The reason that is happening is because in history, most of the electronics were all analog. I've kind of talked to you about that, where a lamp and a radio, all these types of components, or electrical devices, they're all analog. So they do the same thing no matter how long they're plugged in.
Okay, never mind.
Today, it's difficult to find an electronic device that does not have some part of its design that's digital. In some way, shape, or form, you will have some sort of programming or digital component in most electrical devices at this point. I mean, you'll still have lamps that don't, but you'll also have smart lamps that do. So, just kind of depends. There's a few major breakthroughs in technology that we need to know about. Those 5 right there are a majority of the advancements that we need to know. Major one is the transistor right there. That's number 1. You don't necessarily have to write on what's in parentheses.
So we just write the chain.
You can just write what they are: transistor, microchip, CD, DVD, Blu-ray, fiber optic cable.
What's that?
Fiber optics?
Yep.
It's basically signals using light. So they travel at the speed of light. What's that?
Let's write these down.
Yeah, write those 5 things down.
Oh, those copies?
Yep. And then wireless technology. Those are the 5. Check out that awesome flip phone.
Yeah,
Bet y'all wish you had that.
I did have one of those before.
Does it?
Yeah, I have one at home.
I had one of those before.
Flip phones.
Are they?
Flip phones are a fancy company.
Flip phone. I used to have a flip phone.
Get in here, your fancy flip phone.
I think so. I think Samsung's supposed to be coming out with one.
Oh, no.
Oh, yeah.
Imagine Apple coming
Wait, I
out
think they
with
already did. The Samsung Fold. Did it ever come out?
one. I don't know.
And the screen actually folds?
Yeah. Imagine Apple coming out with flip phone.
Why? Why would we want to imagine that? Then we'd have to buy another Apple product.
Oh, what?
Oh, I mean, everybody loves Apple.
Another Apple what?
Yeah.
Another Apple. I actually didn't hear you.
Huh?
Another Apple what? An Apple car?
Product?
Oh.
No,
These Apple cars.
I don't mind. I don't mind Apple. I just don't like the Apple Store, and
buy
and
everything on your phone.
like you can only buy from the Apple Store, which I don't like.
You buy everything on your phone.
With Samsung, at least you have multiple venues you can go get the
You get free apps.
apps from. Yeah.
I mean, you got free apps.
Yeah, sure, buddy.
I mean, I'm sure that some of them are free, but
I mean, I feel like
I would rather pay the person that is designing the app than pay the company that owns the Play Store to have the app. But, I mean, Apple didn't make half those apps. They just made a store and then charged people to put their apps on it. That's just me. That's just me, in my opinion.
They have an Apple Arcade where you have like a whole lot of games. You just pay Apple Arcade for
Like a monthly fee.
yeah. I was like,
That
I'm
sounds
not doing
interesting.
that.
Okay.
They have some good Apple games on it though.
Moving forward, why are digital devices important? Basically, all of the newest technology uses it. So when you are purchasing these new devices, if we hadn't had those advancements, then you wouldn't have these types of devices. So you don't need to write anything down on this one. So what do electrical engineers do?
Write this down.
I would, yes. Electrical engineering is the branch of engineering that deals with the technology of electricity, especially the design and application of circuitry and equipment for power generation and distribution, machine control, and communications. Basically, if it deals with electronics at all, an electrical engineer is probably going to be the one that has to help design it. Usually you work with a team of other engineers, unless it's fully electronic only, but
You short that first sentence down
yeah. I mean, it's all one sentence.
to the first column.
Electrical engineering is where it's at. Not because I'm prejudiced or anything, just because, you know, that's what I did.
Wait.
be a NASA
So we just stop at technology.
NASA engineer.
Okay.
Had a NASA scholarship. Yeah, my freshman year, I lost it.
Did you go to NASA?
No, it was just they paid for part of my school,
You should have went to Mars.
but then I lost it first year, so
How?
I wasn't very smart.
What'd you do? What did you do?
I didn't do. It's what I didn't do, not what I did.
Let me guess, you blew up the science lab.
No, no, I didn't even make it to science lab. Don't be like me, guys.
What'd you do?
All right.
So we won't do it.
Go to school. Go to class.
What?
I didn't go to class. That was my problem. Huh? Yeah, I found other things to do instead of going to class, and that was a bad thing.
Probably in the Mars project right now.
When you get to college, you'll find out. They have like a rec room where all the kids go hang out. Everybody just kind of plays video games and plays pool and just hangs out, watches TV. Unfortunately, that was more important than going to class, evidently. So Don't do that. Okay. Who works with digital devices? Obviously, the electrical engineers do. But also you have the technicians that will be fixing that particular type of technology, and you also have the programmers that help program that kind of technology. So, and you work with these guys pretty regularly. Some students have studied electricity and circuits in other classes. What makes this different? This is an engineering course, not a science class. So scientists are going to ask questions like what are the laws of nature that make it possible? And then an engineer is going to go, I know that this is true because of my science class. How can I use this to make it better, to make something better? And that's kind of how that's the kind of the difference. So in science class, you're learning that's something that's happening, and then in engineering, you are using that knowledge to make something that we need or something that's better. A starship? So you can go to the stars? All right. Moving forward. Okay. Progression of design of digital design tools. This is a transistor there at the top. That's what they look like. From the transistors, we were able to get operational gates or op-amp gates. Oh, my bad. Then you go to integrated chips, which basically the chips have the gates in them. Then you go to a PLD or a programmable logic device, which is basically a programmable integrated chip, which they used to be called PICs, PIC, programmable integrated chips, and then they changed it to programmable logic devices because they do more than just a chip. And then you get to go into microcomputers or controllers, much like the Arduino that's sitting there. And that's where we're at. That's basically a mini computer. If you don't know what an Arduino is. What's the other one? There's the Arduino, and then there's the, I don't remember what it's called. But it's basically a mini computer about the size of a wallet. Yeah, it's about this big.
Like a watch?
It's bigger than a watch.
Apple Watch.
But no, it's not a watch. It's an actual computer. And
The camera.
it just doesn't have a screen. I don't remember what it's called, but I'll figure it out. I have one at home, and I'll let you know. Bring it? Yeah. Okay, so in this class, you're going to learn how to design circuits. You don't need to write anything down on this one either. But that's basically what we're going to be doing. You're going to learn how to design them, learn what we do different or what you change in order to get a different output, things like that. And then understand that the invention of the transistor is where all this technology is coming from. We already kind of did this, so we're going to skip that. And that's it. That's it for that one. Uh-huh.
Can we take a picture to your camp?
Who's going to know? Oh, wait, hold on. Sharing is paused because I minimized.
Uh-oh.
Okay, so how do I do that? Where's your shared window? Sharing is paused until you return to the shared window. This one?
Probably the window that you came from.
Okay, so now I'm going to stop sharing for a second. And then I'm going to go back and share the next one, which safety. Because we need to know how to be safe.
I don't need to know how to say. I'm already safe. I was born safe.
Okay,
I'm militant.
so next topic is safety.
Listen, I was born safe. So, were you? Yes, my militant is safe.
Yeah.
And I was born in a safe.
You were born in a safe and you were safe.
Yes.
All right, this is the next one, guys.
So we just put safety
Yes,
or not?
safety.
How many?
Does everybody see that online? Safety.
I heard. I put my contacts in the second period.
All right. Here we go. We're almost to the point where we're going to be talking about a lab, so that's good. After safety, we have basically we do we start doing the stuff on the lab. Yeah.
This presentation will review general safety rules for the classroom.
That's nice. Okay, safety. Here we go. This presentation, we're going to review general safety rules for the classroom and safety rules specific to electrical injuries. These are things we're trying to avoid. Okay, you're going to want to write down the safety rules. There are 14 of them, so you can paraphrase. You don't have to write word for word, but you do need to write these down. So, number 1, follow all written procedures. That's important. Follow all written procedures. Number 2, you need to read the manuals, the material safety data sheets, which we'll talk about, and we'll use those throughout the class. Other documents that discuss specific safety precautions related to the equipment.
Do they have like a speak button where they speak to us?
Who?
Like the manuals?
No. You got to use your eyes. You got to read, not be read to.
That's easy though.
All right. Number 3, do not disable safety lockouts, grounding prongs, or other devices that would prevent injury.
I read this in OSHA before.
I'm sure you have. If you got to the electrical portion of this of OSHA, you'd probably see a lot of these. By the way, if you're in IED, you should be getting really close to that electrical portion. I think that one's due this week.
I got to that one like
On Thursday, I think.
back in March when it was assigned in November. Right? November? Yeah. It was assigned in November. I got that in March, I believe.
Yeah, it wasn't. I don't think it was assigned until January. I don't think we got it until we got back from winter break.
I thought it was. Okay, I thought it was.
All right, moving forward. Number 4, avoid damp and wet areas when working with electricity. Electricity and water don't mix.
I do all the time.
Avoid wearing jewelry or baggy clothing, anything that could potentially knock something off the table, like a hot soldering iron, which I had a kid do that once.
They knocked the soldering iron?
He knocked the soldering iron and then he went to try to catch it. And I was like, don't. It's already going to hit the ground. Let it hit the ground. You want to try to catch a hot soldering iron with your hand.
Did I tell you that I burnt my dad's toes with my soldering iron?
No. But what were you doing near like a water hose anyway?
No, it was in the garage. I was soldering something together. And I was like, and it dropped. I was like, oh no, and it burned the hose.
I had 2 years ago, I was soldering something and the soldering iron caught the side of my shirt and burned a hole right through it. And I was like, that's not cool. But, all right, number 6, assume circuits are on. Always assume they're on first. And then check the voltmeter to make sure that they are not on before you start handling the wires. Number 7, broken or damaged tools should be labeled damaged and then given back to the instructor so they can be replaced.
Assume circuits are on.
Yeah, always assume circuits are on. One of the biggest things that you'll find out is when you're making your circuit or you're wiring up your circuit, if you haven't finished and you put power to it, sometimes you'll end up with fried chips and things like that, and you'll have lots of problems with that. Then you got to go through and try to figure out where you went wrong and why your circuit doesn't work. And that's what takes so long in some of these projects, the troubleshooting alone. I had one student finish the project, thought he was done, didn't work, took him a week to figure out where he went wrong. It was a one-day project.
Yeah,
Because
and
what-
it just
because
got
something was wrong.
Yeah, I couldn't figure out what went wrong,
What
so
was wrong?
I don't know. Eventually, after that week of him trying to troubleshoot, I was like, hey, just tear it apart, start over. Normally, we don't do that, but if you've spent a week trying to figure out where you went wrong, you might as well. On a project that should only take you a day, you've done something.
Broken tools should not be labeled. Damn it. Oh, should be labeled, damn it, not used.
So what?
All right.
Order number 8.
What's that?
What the kid that tried to catch us on this?
Oh, he didn't catch it. What? Because I'm sure that I like said something as he was trying to go out and like let it fall or something, and he let it hit, fall, but like he had bent over to try to catch it before it hit the ground.
So you almost got it.
So he almost caught it. He didn't catch it. Luckily, he was a little slower, so he didn't get all the way down there. His reflexes weren't super fast, and
That's a serious thing. How fast reflexes, like when it falls,
yeah, that's your instinct to go catch it before it hits the ground. Yeah, you don't want to do that with a hot soldering iron. Let it fall. All right, have a classmate control the power so that a passerby does not turn the power back on. Somebody that walks by. You don't want somebody to come by and flip the switch on your power supply and turn the power on when you think it's off. Yeah, it's not a good thing.
Who would turn it on though? Like, why?
I don't know. Why do people turn off computers in the classroom? Okay.
We're doing for fun.
Right. Use only the appropriate class of fire extinguisher to put out electrical fires. Class C fire extinguishers are preferred.
I heard this before.
Uh-huh. Again, OSHA. B and D are acceptable and will work. Class A is water, and we do not want to use that one with electrical circuits. It's a bad, bad story. Start using water to put out electrical fires.
I got water. Like, wait, no. Don't do it. I'm looking up the video for the gumbo.
All right.
What about chemical fires?
What about what?
Chemical fires.
Chemical fires, usually I think you use a sulfur, which might be also a class C.
Do I have the right number 9? Because it's too much right now.
No, you need that. You're gonna wish you had it.
But we don't have a fire extinguisher in here.
It's right across the hall.
Yeah, the girl with that fire, just to get.
It's right across the hall.
It needs to be in here, Mr. Wilson.
Huh?
It needs to be in here.
Yeah, these are being.
Well, I don't know. It's right across the hall. Do what?
Gonna start a lot of fires so we get that in here.
We have fire alarms.
But it'll alert the whole school.
I think those white things right there are the sprinklers that drop down. Like the white caps.
Oh, that's tight. That's
You can test it out.
No, I don't want to test it out. We'll just assume.
I wonder what's like that being.
All right. Why that didn't go to the next one, I don't know. What's going on? Oh. All right, use chemicals as directed on the container. We don't use chemicals in here, so. Do not use any tools or equipment until instructed on their purpose, on their proper use. Somebody's in the lobby.
Yeah. Or that's either amendments.
Somebody's in the lobby, I think.
Late. Go get 30 pass. Is the 30 pass gone now?
What?
Is the 30 pass station gone?
I don't know. I haven't had anybody tardy.
You never counted it starting.
I counted some people tardy.
Last year you did it. Not me.
Maybe not you, but I did others. It depends on how late you are. Use safety glasses, or goggles, not normal eye reading glasses around chemicals that may splash or objects that can be thrown.
Turn it, my bad. Turn it.
We use safety glasses when we're soldering, majority of the time, actually all the time when you're soldering, if you don't want solder to splash.
I learned this in the.
Huh? Solder is melted metal.
I learned this in the technique.
Yeah, did y'all get to solder anything?
No, we did a it's like a test on it, like safety procedures. That's it.
Yep.
Can you imagine the kids saying you to be assaulted? You assaulted to get your haircut, you think it's going to need clippers?
Next, number 13, take your time. Most accidents occur whenever you're in a hurry. Number 14, always keep the laboratory clean and neat. You don't want to trip over stuff. It's a lot of this
Clean
is
shop is a safe shop.
same, yeah. It's a lot of the same kind of things you would find in the OSHA if you're doing OSHA.
Wait, if you have OSHA, would we go for everything? Like everything, like science and everything else?
Yeah.
Or engineering?
It's general industry.
Oh,
That's what you took last year, so that goes for everything.
oh
I got a
yeah.
question about OSHA. When it expires, you have to retake the course?
Yes.
My understanding is that you do not have to retake, it's just a renew. So you
We
might
did this
take,
stuff in the beginning anyway.
but I don't think you have to do another 30 hours. But I don't know. I can't guarantee that because I thought it was a lifetime membership or a lifetime thing, but you just had to renew it every 5 years. That was my understanding.
Oh, wait, I gotta write this stuff down, hold
No, I want to find that out, because I want to do a whole 30 hours.
on. 30 hours shouldn't be that.
Well, you'll
long.
get it for 5, at least you don't have to do it for 5 more years. And then by then, hopefully you have a job that pays for it.
Please.
So you don't have to pay.
Nice paying that for 5 minutes.
All right. This is something you kind of want to write down. You can phrase that in your notebook as a form like that if you want, or a chart if you want to, but we need to know those numbers. This is how much current and what that amount of current will do, or what it feels like. Okay, so starting with the top, 1 milliamp. 1 milliamp,
Write the chart down?
huh?
Write the chart down?
Write that chart down, yeah. Yeah. You can paraphrase the stuff on the side, but most of it's already paraphrased, so. 1 milliamp, with 1 volt, or requires 1 volt or 100 volts, somewhere in that area, depending on the resistance that you have. And if you look at the top, it kind of tells you that the resistance of dry skin is anywhere between 1,000 ohms and 100,000 ohms.
Pain.
But basically, at 1 milliamp, the threshold of feeling tingling sensation, so you might be able to tell it's there.
Like chopping down.
So you may feel it, you may not feel it. Yeah, like kind of like the shocking gum. I think the shocking gum might be a little bit higher because you can usually feel that.
Yeah, you can use
Yeah. At 15 volts, this is the maximum current that a human can withstand without withstanding injury.
Why?
So this could be similar to like
To the bottom.
like the household 110 voltage. You'll feel it, it'll tingle, but it won't
Or like,
injure you.
we can't go above 5,
15?
15.
15, that's when we're looking at the current. Current is the thing that we're paying attention to the most.
6, 8.
Anywhere between 15 and 20 amps, this is where you start having muscular contraction. Basically, your hands tighten up, or whatever's touching the electronic or the electricity. Basically, it will tense your muscles, and you can't let go of stuff. So that's how the beginnings of electrocution type start. So you have to be careful.
So, it's like
Electric fence, you can kind of feel it with an electric fence. It's enough to make your hands like contract. It's usually not quite there, so usually you can let go, but 10 or 100 to 300 milliamps. You have ventricular fibrillation. Basically, you'll have issues breathing and things like that. Well, actually, this one at this point you're still able to breathe, but it's on that verge. So yeah, and if it keeps going, then you can die.
Do we go above 15?
Do we?
Yeah.
Never. We don't go above 1. Yeah. We use we use 5 volts sometimes, but that's about as high as we get. So we're on the low end of that 15. So the maximum you'd be looking at is maybe 5 milliamps. But I have never heard of anybody in my classes yet get a shock, other than the kid that puts his tongue on a 9 volt. You know.
Somebody did that?
People are weird. So if you get up to 6 amps, this is where you're going to have respiratory paralysis. Your lungs are going to stop. You're going to end up with getting burned and different things like that, and your heart's not going to be able to handle that. So it's bad. It's bad news. Bad news. Stay away from that. 6 amps. Actually, 1 amp. Stay away from 1 amp. Huh?
Who goes above 15?
Milliamps?
Yeah.
Electricians.
Colleges?
Electricians do. You don't want to touch a 220 in a house because that's over 220 volts at a house. It's going to be over that 15. You don't want to touch that. You don't want to be messing with that. Don't mess with anything in your house that's got the bigger plug on it that's like that. Just leave that alone.
I don't see that.
Just leave it alone.
What would it be?
Just depends on whether or not you have a electrical house or a gas house. Some people have gas. They use gas.
I don't know.
Yeah. But stay away from it. If the plug doesn't look like a normal wall plug, just stay away from it.
So how would the volts be that you fly? Like when you touch and
That's the 220. Yeah. Yeah, you don't want
I
that.
actually want to touch it though.
You don't want to be anywhere around that.
it's funny because it's really a movie.
Uh-huh. Yeah.
Movies are not real.
Movies are not real. Somebody had to remind them. It's okay. All right. Moving forward. Everybody get that chart?
Almost.
If not, you can pause the video because I'm recording and go finish the chart. All right. Burns, electrical burns. Electrical resistance produces heat. The more current, the more severe the burn you're going to get. Shorted components will burn you on contact because they get hot. Normally, if in this class, if you get an injury, it's probably going to be a burn, and it's probably going to be from a component being wired in incorrectly, and you burn your finger. It's usually what any of the injuries that we've had in the class, that's usually what they are from. And then, of course, soldering irons, but most people are careful with their soldering irons. So,
I'm not.
They're just scary.
right, because I mean they are. It's good to have a fear of soldering irons. They're super hot. You don't want to touch them.
It's like an iron.
I've got
It's a hot piece of metal that melts metal. I mean, it's going to be hot. So you don't want to touch one to find out how hot they are. You just have to know, oh, it's melting metal. It's going to melt my skin. We're good.
I tried that before.
Yeah,
I touched the soldering iron.
no, not.
So I did not have now.
All right. Anyway, chemicals, smoke from burning or melting components. When we solder, I put on fans to make sure that there's no fumes lingering while we're doing the soldering. And I have the filter in the back that will turn on to make sure that there's no fumes, because we don't want anybody getting sick. Worst case scenario would be you get a headache, but we don't want that either. So older lead-based solder can have more chemicals than the newer stuff that we use. And then the printed circuit board etching materials, we don't even do that. here at this school because it's a chemical that burns through metal. We don't deal with that. So, just dangerous, you know. It's not something that we need to do. We don't need to, we're not making printed circuit boards here at school anyway. We're dealing with programming of the components, so we use breadboards the whole time.
Breadboards are outfalling.
Breadboards are amazing. All right. Electrical injuries, wounds, small wires can puncture the skin. We use small wires, so you have to be careful with that. Every once in a while, somebody will get a wire poked through by their fingernail, and that hurts. When you pull out integrated circuits or the ICs, a lot of times if you don't pull them out right, they can stab you in the finger and the thumb. But I show you how to do it correctly, so as long as you take the time to do it right, you won't ever have that issue. Sometimes when you cut wire, small pieces of wire can fly off and hit somebody in the eye. But I teach you again how to cut the wire correctly so you're not cutting wire and making it fly around. So it's usually not an issue.
I actually like this.
But-
This book is actually cool.
The what?
This book, like, it's already numbered and everything.
Oh, I know.
Like,
You're
it's-
welcome.
It's so much better.
I sat there and did that for like an hour, made sure yeah, I made that.
I thought OSHA did this.
Nope, I did that. And you're welcome.
Well, I'm not welcome anymore. Because you did it.
Oh, that's why it says Braswell on the front.
I thought you just like ordered this.
It's,
from
and it says my name on it.
I thought you ordered it from somewhere though.
Oh,
Like somebody, you just had to get it printed off and stuff.
I had to make it and sent it off to get published, yeah, whatever, to get it printed. All right.
Like 1,000.
Purpose of that presentation was to review some of the potential risks associated with working with electricity in a classroom. The likelihood of these injuries happening is remote, but it's your responsibility to follow the rules. If you see a classmate not following the rules,
You slap 'em.
remind them.
You slap 'em.
If they are purposely not following the rules,
You slap 'em.
Snitch.
report them.
Before OSHA, I got his number. I got OSHA's number.
Yeah?
Yeah.
Like, you know, like OSHA violation.
At Braswell High School.
That's a little OSHA violation.
All right. I believe this is it. Yep. Okay, so that's the end of safety. I am going to stop the recording so that I can get the video from right there. So we're going to stop that recording.